Today we're going to discuss improving Euler's method. Before we do so, let's review some ideas from before about numerical error in Euler's method. Throughout the course, we've considered initial value problems in the form dy dt equals f of t comma y, where y of t0 equals y naught. Here, y is an n-dimensional vector. In Lesson 5, we proved the so-called existence uniqueness theorem, which says on a certain rectangle, if we have conditions where f is continuous and df dy is continuous, then there exists an interval I such that we have a unique solution y of t. This is at least for one-dimensional systems, although in Lesson 15 we stated a similar statement for two-dimensional systems. The issue here is that only in a few cases can we explicitly find the solution y of t. Instead, we look for approximate solutions. Let's consider a one-dimensional system of the form dy dt equals f of ty, where initially y at t0 equals y naught. Fix a step size h and perform the following steps. First, compute the slope f of tk yk. Second, compute the time t sub k plus 1 equals tk plus the step size h. Third, compute the value y sub k plus 1 equals yk plus the slope f of tk yk times the step size h. And fourth, return back to step 1 with k replaced by k plus 1. In plotting the points tk, yk, we would find an approximate plot of the graph of the actual solution y of t. This technique for finding an approximate solution is known as Euler's method. Note in Lesson 14, we generalized this to two-dimensional systems by introducing Euler's method for systems. Our main result is as follows. Consider a first-order equation again and say that there is some rectangle R such that f is continuous on this rectangle, the partials df dt and df dy are also continuous on this rectangle, and our initial point t0 y0 is in the rectangle. Moreover, say that we have an approximate solution, namely points tk, yk, which give us an approximate solution coming from Euler's method for step size h. Then there exist constants m1 and m2 so that the error term y of tk minus y sub k is less than or equal to m1 over twice m2 times the exponential e to the m2 times b minus a minus 1 all times the step size h. Notice that the total error, e sub k, just depends upon the length of the interval from a to b and the step size h. In particular, if the step size is decreased, then the error decreases linearly. That is, we have a bound of the form e sub k is less than or equal to a constant c times the step size delta t. Today we will discuss improving Euler's method, and we're motivated by the following question. Does there exist another algorithm which gives us a better bound on the error? In order to gain some intuition behind how we should improve Euler's method, we'll discuss how we investigated the error in Euler's method in the first place. Recall that we proved the following. If y of t is the exact solution, then we can use a Taylor series expansion to find a constant m sub 1 such that in absolute value, y of t plus h minus y of t minus f of ty times h is less than or equal to m sub 1 times h squared. Using this, we see that if we have a point tk, yk that's very close to the actual point tk, y evaluated at tk, then the new point t sub k plus 1, y sub k plus 1, which is defined as tk plus h, yk plus f of tk, yk times h, is also close to the actual point tk plus 1, y evaluated at tk plus 1. By considering the Taylor series expansion in a bit more detail, we can find a different constant m sub 1 such that we have the following inequality. In absolute value, y of t plus h minus y of t minus the ratio f of ty plus f of t plus h, y plus l, all divided by 2 times h is less than or equal to m sub 1 times h cubed. Here, L is f of ty times h. Using this, we see that if the point tk comma y sub k is very close to the actual point tk comma y evaluated at tk, then the new point tk plus 1 comma yk plus 1, which is equal to tk plus h comma yk plus the following ratio, f of tk yk plus f of tk plus 1 y tilde k plus 1, all divided by 2 times the step size h, is also very close to the point, the actual point, tk plus 1, comma y evaluated at tk plus 1. Here, y tilde is the value y sub k plus f of tk yk times the step size h. Using this concept, we're going to introduce the following algorithm that we'll call the improved Euler's method. Say that we have an initial value problem coming from a one-dimensional system. dy dt equals f of ty, where y of t0 equals y0. Fix a step size h and recursively perform the following 6 steps. Number 1, compute the slope m sub k, which is f at tk comma yk. Number 2, compute the new time tk plus 1, which is tk plus h. Number 3, compute y tilde k plus 1, which is yk plus mk times h. Number 4, compute a new slope m sub k, which is f evaluated at tk plus 1, comma y tilde k plus 1. Number 5, compute the value y sub k plus 1, which is y sub k plus the ratio mk plus nk over 2 times h. And last step, return back to step number 1 and replace k with k plus 1. This technique is known as the improved Euler's method or the modified Euler's method. Some texts call this Hoyne's method after the German mathematician Karl Hoyne, and yet other texts call this the second order Runge-Kutta method after the German mathematicians Karl Runge and Martin Kutta. Before we move forward, we'd like to give a geometric interpretation of what's actually going on here. Let's say that we'll start with the point tk comma yk. Euler's method predicts that the next point, that is the Euler point that you see here in the diagram, will be tk plus h, comma yk plus mk times h. Here, mk will be the slope of our initial point, tk yk. However, the improved Euler's method corrects this by averaging with a corrector point. In this case, the corrector point is given by tk plus h, comma yk plus nk times h, where nk is the slope that we had from the Euler point. That is f evaluated at tk plus 1, comma y tilde k plus 1. You can see here the points on the graph at the top of your screen. When we say average, we mean that this here we'll call the Hoyne point. Again, this is the average of the Euler point and the corrector point. This is simply tk plus h, comma yk plus the ratio f of tk yk plus f of tk plus 1 y tilde of k plus 1, all divided by 2 times h. In other words, the improved Euler's method is a type of a predictor-corrector method. Here, the Euler point is what we predict coming from Euler's method, but in some sense, we haven't really found the correct point. So we have to correct our prediction by this idea of a corrector point. Now, taking the average of the two, this is the so-called predictor-corrector method, we find the Hoyne point, which is really the correct point that we should get that's a little bit closer to the actual solution. Let's give some examples of all of this in practice. Let's consider the first order equation dy dt equals 2y minus 1, where y of 0 equals 1. We know that the unique solution to this initial value problem is y of t equals e to the 2t plus 1 divided by 2. First, let's take a look at the scheme we find from Euler's method. If we have a step size delta t, we can then write tk plus 1 is tk plus delta t, and yk plus 1 is yk plus f of tk yk times delta t. Here you can see up on your screen all of the numbers that we would find if we have a step size of 0 0.1. You'll notice here by the time we get to the bottom of the screen, the error term is 0.59866. Instead, now let's consider the improved Euler's method. Again, the differential equation is the same, and we have our unique solution, but now the scheme to actually find tk plus 1 and y sub k plus 1 is a little bit different. Here you can see tk plus 1 is the same as before. We have a slope m sub k, that will be our predictor slope, but then we have to be careful because we have a point y sub k plus 1 tilde, which really tells us that this is now our corrector point. We can then compute n sub k, which is the slope of the corrector point, and therefore y sub k plus 1 is now the predicted corrected point that we should have. Here you can see on your screen all of the numbers that we should find once we run through the improved Euler's method. In particular, you'll see at the bottom line that the error in the lower right-hand part of your screen is now 0.0422. This is much smaller than what we had before on the previous screen. In fact, you can put all of this together to take a look at the graphs. Here, the blue lines will be the plot of the actual solution. Y of t is e to the 2t plus 1 over 2 versus the gold dots, which would be either coming from Euler's method, that's what you see on the left, or the improved Euler's method, this is what you see on the right. You can really see that Euler's method does have an error that seems to creep along as the points, as k increases. Whereas for the improved Euler's method, we seem to be doing much, much better of following along the actual graph. This means that the improved Euler's method seems to have a much, much smaller error compared to Euler's method. So is there a way that we can actually quantify all of this? That is, our motivating question is, can we measure the error and how it grows as a function of the step size h? Here's our main proposition. Let's consider an initial value problem. dy dt is f of ty, where y of t0 equals y0. Let's say that there's a rectangle R where three things are true. First, f is continuous on R. Second, the partial derivatives d squared f dt squared, d squared f dt dy, and d squared f dy squared are all continuous on this region. And third, the initial point t0, y0 is in the rectangle. Also, say that we have a collection of points tk, yk, which gives an approximate solution coming from the improved Euler's method for step size h. Then there exist constants m1 and m2 so that the error term, namely the absolute value of y evaluated at tk minus y sub k, is less than or equal to m1 over m2 times e to the m2 times b minus a minus 1 times h squared. Notice that the total error, just like before with Euler's method, depends upon the length of the interval and the step size h. However, in this case, something crucially different is true. If the step size is decreased, then the error decreases quadratically. That is, we have a bound in the form e sub k is less than or equal to c times delta t squared for some constant c. We'll spend the remainder of the time sketching out the proof of this proposition. We'll do so using a series of three lemmata. First, we claim that there exists a constant m sub 1 such that you have the inequality that you see here on your screen. To explain why this is true, first, let's say if y of t is an exact solution, then we have the following derivatives. That is, we have here y prime, which is just f, y double prime, which we can write as these partials, df dt plus f times df dy, and the third derivative now is a much more complicated formula, but we can still express it in terms of various partial derivatives of f. Putting all of this together, we find the following Taylor series expansion. That is here y of t plus h we can write in terms of y of t plus y prime of t times h plus y double prime of t times a squared over 2 plus y triple prime of t times h cubed over 6 and so forth. Using the substitutions on the previous screen, we can write all of our functions here in terms of this f and its various partial derivatives. This means that we have the following inequality. If you'd like to see where this is coming from, first, notice that we can subtract various forms from one side. Also notice that here we have constants m1 and m2 that you see here defined on your screen. Here, if we take the left-hand side minus the first few terms of the right-hand side, we find the quantity inside of the absolute value sign. The m sub 3 is this collection of second partial derivatives, and the m sub 4 is this product that appears just before ace cubed over 6. We can perform a similar Taylor series expansion once we consider this f as a function of two variables. Now let's substitute L, which is f of ty times h, and we find a slightly different formula, but this almost looks the same as what we had on the previous screen. The difference is we need to multiply by h over 2 to find the following inequality, where the m3 is exactly the same m3 as before. Notice that here, this inequality comes from taking a look at the left-hand side minus the first two terms on the right-hand side. And the m3 is just the expression that we have in front of the h squared over 2. Finally, if we combine this with the inequality that we just stated on the previous screen, we can use the triangle inequality to find the desired inequality from lemma number 1. Here, notice that the constant m sub 1 we can express in terms of m sub 3 and m sub 4. For the second result, we claim that there exists a constant m sub 2 so that you see the expression here on your screen. This is a matter of explaining how the error terms change as we increase k. Notice that the improved Euler's method asserts that tk plus 1 is tk plus h, and yk plus 1 is yk plus this ratio f of tk yk plus f of tk plus h, comma, yk plus L, all divided by 2 times h. This is in terms of L, which is f of tk yk times h. We're going to play out the fact that we really do want f of tk comma y evaluated at tk, so let's write down the following rather complicated identity. This here has 4 terms in the square blocks, and we'd like to bound each one of these by an inequality. The first one is just a restatement of lemma number 1 in terms of our constant m sub 1. For the second and third terms, we realize that we can express now our inequality in terms of m sub 2, which is just the max of the absolute value of the partial of f with respect to y. For the fourth term, we can now use this inequality repeatedly, and we find, putting all of this together, the inequality that we claimed for lemma 2. For lemma 3, this actually is the statement of the proposition. First, we'll show by induction, just as we did with the Eulers method, that the error term here is less than or equal to capital K raised to the lowercase k minus 1 divided by capital K minus 1 times m sub 1 times h cubed. Simply put, we can prove this by induction, but the proof by induction follows almost exactly word for word as in lesson number 37. So now let's finish off the proof of lemma 3. Say that we divide the interval from a to b into capital N equal parts. That is, our step size h will be b minus a divided by capital N. As we found in lesson number 37, the largest error is just going to come from the difference ytk minus yk when k is equal to capital N. So we have the following inequality when k is equal to capital N. We can express this in terms of an expression involving x, which is m sub 2 times b minus a. Now, we simply realize that the max that we can have for this expression, raised to the nth power, for any non-negative integer n, is going to be e to the x, which actually gives us exactly what we wanted for lemma number 3. So this suffices then to show that the max here is really e to the x. In fact, we're going to write down a more general statement. For any positive integer m, we have the following. We'd like to consider the max of this collection of numbers, where c of n is this sum here. We claim that this is equal to this limit as n increases without bound. This is true because the C sub n's define an increasing sequence. Now, let's substitute 1 over n is just equal to epsilon and realize that as n increases without bound, epsilon must tend to 0. But now we'll just simply express this as the exponential of something, and let's move the exponential outside of the limit as epsilon tends to 0. Here, if we take the limit as epsilon tends to 0, more or less we can plug in epsilon is equal to 0. But there's a small problem because we actually find the natural log of 1 divided by 0, which is an indeterminate form. So we'll use L'Hopital's rule to simply take the derivative, and now if we take the limit as epsilon approaches 0, we find e to the x. But this proves exactly what we claimed earlier. Thanks very much for watching.